Okay, so we'll continue on here. All right, so we left off talking about sampling distributions, and we said sampling distributions will follow the normal model as long as your sample is large enough. No matter what your population looks like, your sampling distribution will follow the normal model as long as your sample is large enough. There is another, I guess, thing that goes along with it. So let me just list off all the conditions necessary, okay? The central limit theorem applies when, okay, samples are taken randomly. So that's our first assumption. Samples are large enough, and that includes, that means if the population is normal, any sample is large enough, and if it's not normal, you need, the rule of thumb is 30 or more. That will suffice for most cases, or even more if it's really skewed. Okay, samples are large enough. And then one more is that the samples cannot be too big. Okay, the sample is not too big, which applies if you're sampling without replacement. Okay, so that is, do not sample over 10% of the population if you are sampling without replacement. If you're sampling with replacement, you can take as big of a sample as you want. Okay? But if you're sampling without replacement, don't sample more than 10% of the population. Because what happens is when you start to take such a big sample, you actually start to affect what remains in the population. So you can imagine if you have a deck of cards, the very first card has a 50% chance of being red, right? 26 of the cards are red, 26 are black. But after you take your first card, the second card technically doesn't have a 50% chance of being red anymore. There's only 25 red cards and 26, and there's 26 black cards. Okay. So what we're basically saying is that when you're sampling less than 10% of the population, the amount it changes is small enough that we can ignore what happens. But when you start to take, a whole bunch of cards out of the deck, or you're sampling more than 10%, what remains in the population could be affected by what happens in your sample. Okay? And that's if you're sampling without replacement. If you sample with replacement, you take a card out and then you put it back into the deck, you're always going to have a 50% chance of selecting a red card, 50% chance of selecting a black card, because every time you put the card back in, you're resetting everything. You have 26 red and 26 black cards. But when you're sampling without replacement, you don't want to sample too much. This is generally not, like on a practical level, you don't run into this very much, okay? Only if you're like trying to take random samples from like an institution like a company where there's a limited number of employees, maybe you don't want to sample too many, okay? But this is usually the one you run into. Samples are large enough. That's the one we have problems with. Okay. And the central limit theorem is strong enough to hold when our population is categorical, at least when there's two categories. And that's what we saw with the binomial distribution and the normal approximation to the binomial, which we did last week. Basically, if the population no longer we're talking about a numeric variable, but we're talking about a categorical variable. And if we say population is 70% yes and 30% no, okay, you know, every time you take a sample, maybe I take a sample of 20 people, maybe in this sample I get 15 yes and 5 no, all right? Well, this is essentially just a binomial problem, okay? We're taking samples of n equal to 20, you know, p is equal to 70%, that's what we have in the population, and here j is equal to 15, okay? And what we see is that when we have a situation like this, and actually 20 people is a little bit small, but we end up getting something that looks like a normal distribution. And we saw this last week when we did the normal approximation to the binomial. Okay. All right, but going back to the numeric variable, numeric variables, just keep in mind that because of the central limit theorem, we know that y bar comes from a normal distribution with mean mu and standard deviation sigma over the square root of n. Okay. That's the essential, that's the big thing that we're drawing from chapter 5 on sampling distributions. We know that when we take a large enough sample from any size population or any shaped population, that sample mean comes from a normal distribution. We know that. And so we have an application for this. Okay, and this is, we're going to enter chapter 6 now. Here, our application of the central limit theorem. And it's actually sampling distributions and central limit theorem, all of this. It gets applied in chapter 7 with our t-tests and everything in the future and so on and so forth. But this will be our first application. And we are making confidence intervals. So everyone's good with central limit theorem, chapter 5? We're good there? Okay. All right. So over here we said, basically when we're saying that y bar comes from a normal distribution with mean mu and standard deviation sigma over the square root of n, we're essentially saying we know what the population looks like. We're saying we know the population has mean mu and the population has standard deviation sigma. But in real life, we generally don't know what the population looks like. Okay. We might want to know what the mean of the population is. Okay. And so a confidence interval, we're saying with a confidence interval, we do not know mu or sigma. Okay. So these are, we don't know the mean or standard deviation of the population. So, but if we observe data, observe a sample of data, can we then make conclusions about the population? spoiler, the answer is yes, but how is this going to work? Okay. So again, we don't know the mean or the standard deviation of the population. What we can do is we observe a sample, a random sample maybe, or yes, a random sample, and based on this random sample, what kind of conclusions can we make about the population? All right, and so to explain what we're going to do, we're going to put this thought on hold, and I'm going to draw a picture. Okay. So imagine this being posted on Instagram or whatever. It's Super Bowl Sunday this weekend. So, all right, let's say we've got this. We're at the 30-yard line. Okay. And what you see is here's a doggy. Okay. Okay, and so it says. Not hashtag, but we'll say dog at the 30-yard line. Where is the owner? Okay, and we hashtag he's invisible with invisible leash. All right, so this is a picture of a dog at the 30-yard line, but the owner is invisible, and the owner has an invisible leash. So the dog is actually on an invisible leash. Okay? And we actually know a little bit about the behavior of the dog and the leash. The dog, likes to explore and wander off, but it also doesn't like to strain that hard against the leash. And so we say, based on the what we know about the dog and the leash, we say about 68% of the time, the dog remains within 1 yard of the owner. And about 95% of the time, dog remains within 2 yards of the owner. And about 99.7% of the time, dog is within 3 yards of the owner. Okay? So this is what we understand about the dog. Okay? Dog doesn't like to wander too far away from the owner because he has an invisible leash. Okay, so based on what we see the dog at the 30-yard line. What can we say about the location of the owner?
He's not more than
Somewhere between 29 and 31.
Is the owner between 29 and 31?
27 and 33.
Is the owner between 27 and 33?
99.7% chance.
All right, so so we can say something like, I'm pretty sure the owner is between 27 and 33. But is it possible that the owner is at 26 and a half? Yeah. And what does that mean about this picture? Well, it just means the owner could be at 26 and a half, and it just means we happened to take the picture when the dog was behaving a little bit weird and decided to go more than 3 yards away from the owner. Okay? Normally doesn't do that. 99.7% of the time, The dog doesn't do that, but maybe this picture was taken during that 0.3% of the time. We don't know, okay? So we could make a few statements like this, okay? We could say something like, I'm 99.7% confident that the owner is between the 27 and 33 yard lines. Okay? I could even say I'm 95% confident that the owner is between the 28 and 32 yard lines. Do we feel comfortable with these statements here? Okay. But the owner could be, is it possible for the owner to be at 26.5? Yeah, okay. And the answer is yes. But for that to be, this picture must have been taken at one of the strange times the dog pulled hard on the leash. Okay. So that's the dog with the invisible owner. We can see the location of the dog, but we don't know where the owner is. But because we know about the behavior of the dog, we can make statements about the owner. Our statements about the owner aren't going to be 100% foolproof. Okay, we can make confidence statements about where the owner is located, but we could also be wrong. Okay? So this is analogous to observing a sample mean and making conclusions about the population mean. Okay? From the central limit theorem, we know the behavior of the sample mean. We know that the sample mean will come from a normal distribution centered at the population mean. Okay? So because of that, if we see the sample mean at, say, 30, then we know the population mean should be close to 30. Okay? Because the sample mean doesn't like to stray too far away from the population mean. Okay? That's what we learned in chapter 5 with the sampling distribution and the central limit theorem. Okay? We know that the sample mean, y bar, doesn't like to go too far away from mu. Okay? Even though we have no idea where mu is, when we see y bar, we know that y bar should be somewhere close to mu. Okay? So what I can say is that I can make the same kind of statements about y bar and mu. About mu, the population mean, based on our observation of y bar, the sample mean. Okay. So here I can just say 68% of the time y bar remains within one standard deviation of mu. Okay? Or actually, I'm sorry, not one standard deviation, one sigma over the square root of n, right? About 95% of the time, y bar remains within 2 sigma over the square root of n of mu. And about 99.7% of the time, y bar, not the dog, y bar remains within 3 sigma over the square root of n of mu. So is that transition okay? And this is all based on our understanding of the normal model. So here I made a 95% statement. I said I'm 95% confident that the owner is between 28 and 32. Basically, I can say I am 95% confident that mu is between, I'm going to say y bar plus 2 times sigma over the square root of n and y bar minus 2 sigma over the square root of n. Okay? Or I could just say y bar plus or minus 2 sigma over the square root of n. Okay? So I want to see if this statement of confidence is okay as well. All right. There's a problem here, though. And I don't know if you guys can see it. Can you see the problem with this statement? What's that? Not the and. What do we know about the population? Nothing. We don't know mu, and we don't know sigma, right? And so here I'm saying y bar is within 2 sigma over the square root of n, okay? But I actually don't know what sigma is. So what am I going to do? Okay, yeah, that's what we're going to have to do. We're going to approximate it. And how should I approximate sigma? Yeah, that's a tough question, okay? So our best guess for sigma, which is the population standard deviation, is going to be the standard deviation of our sample, okay? So our problem here is we do not know sigma, population standard deviation. We don't know what that is, okay? So we will approximate. With the sample standard deviation. S, okay? All right, but because we're bringing in another layer of uncertainty, okay, we're going to have to compensate for that. And so instead of 2, we're going to have to put in basically like a fudge factor. Okay, we're going to have to kind of change this number. Instead of saying I'm 95% confident that mu is between y bar plus or minus 2 times sigma over the square root of n, I'm going to have some other number times s over the square root of n. Okay, so I'm going to say, so our statement becomes I am 95% confident, or actually any level of confidence really, 95% confident that the population mean mu is between y bar plus, and then I'm going to temporary placeholder, t star times s over the square root of n and y bar minus t star times s over the square root of it. Okay? Or just simply y bar plus or minus t star times s over the square root of it. Okay? So again, it's based off of this idea, but instead of sigma, we're plugging in s, which is our estimate for sigma. And instead of 2, we're fudging our numbers by using what we call t star. Okay? T star comes from the t distribution. Okay? And the t distribution is basically like the normal distribution, but it has all of these compensation factors built in. Okay? History is from, it was actually developed by a guy working at Guinness Brewery, and he was running into problems with, well, he was in charge of quality control. I don't know about in charge, but he worked in the quality control department, and based on his tests, he was rejecting beer, but then when they tested the beer, it turned out to be okay, and they said, you're giving us problems here. And so he went back and he figured out that he was using the normal distribution when he needed to be using something else, and so he developed the t distribution. So anyway, in the back of your book, and it's probably on the inside back cover, and it's also in your handouts of tables that I provided you. I think table 4 is the critical values of the t distribution. Okay? And the t table is very different from the normal table. Okay? The way the t table works, I don't know, I'm not going to explain the way the t table works today. I'll just explain how to get your t star values for this, okay? So if you want to create a 95% confidence interval, okay, at the bottom you'll see one of the columns of numbers say 95%. And you'll have on the side something that says DF, or degrees of freedom. Your fudge factor here, how much you should change that number from 2 to something else, depends on your sample size. If you have a large sample, you can kind of expect your large sample to give a pretty good estimate of the standard deviation of the population. So the amount you need to compensate is going to be little. If you have a tiny sample size, though, like a sample size of 3 or 4, you can't expect that sample to give a very good estimate of the population standard deviation. So you're going to have to compensate quite a bit. Okay? So that comes into play with degrees of freedom. And so degrees of freedom is equal to your sample size minus 1. Okay? So if you have a sample of, say, 51, okay, so if n is equal to 51, your degrees of freedom is equal to 50, and so you go to 50 degrees of freedom, and for 95% confidence, 50 degrees of freedom, the number you use is 2.009. Okay? So it's not very different from what you would use otherwise. And actually, you wouldn't use 2, you would use 1.96 if you look up your normal distribution. When we say approximately 95% is within 2 standard deviations, it's technically actually 1.96. So you see that when you have a sample size of infinity, that last number is 1.96. Okay. But anyway, sample size of 51, you have 50 degrees of freedom, and so your quote fudge factor, the amount you're compensating is only a little bit, and you would use 2.009. However, if you had a sample size of, say, 3, okay, if n is equal to 3, you only have 2 degrees of freedom, okay? And so the amount you need to compensate is going to be quite large, and so instead of 2, you would use 4.303, okay? So your T star changes depends a lot on your sample size.
So the greater the sample size, the smaller the standard deviation, the more.
Okay, so a few things change. Okay, so if your sample size is big, the standard deviation itself, the standard deviation of the sample doesn't get bigger or smaller. You can't expect that to get bigger or smaller. You can expect it to become a better estimate. Okay. What happens is the square root of n gets bigger, so the standard deviation of your sampling distribution shrinks. Okay. And your t star also gets smaller. Okay. But the amount the t star changes is relatively small compared to the amount it changes over here. Okay, so your t star also changes based on your sample size. Okay, so you make this statement. I'm 95% confident that the population mean mu is between this and that. Okay. All right, so let's try one of these things out. Okay. So earlier I said, you know, I made a bunch of data on the computer about IQ scores and things like that. Okay, and so you know we took a random sample of 10 people. And let's say the mean IQ in the sample is 95.6, and the standard deviation of the sample is 13.71. So if we had no idea what the mean of the true mean of the population was, what can we say about mu based on our sample? Okay, so let's say we didn't know that the mean was 100 and standard deviation was 15. Based on this, what can we say about the sample? Based on this, what can we say about the population? So based on our sample, what can we say about the population? So the idea here is we're going to say, you know, I'm 95% confident, or you know, whatever level of confidence you want, that mu, the population mean, that the mean of the population is between, and we're going to have y bar, I'll do minus t star times s over the square root of n, and y bar plus t star times s over the square root of n. Okay, so take a minute to calculate that out. Let's just make sure our numbers match up. Are we in agreement here? Or did I make a mistake? I don't know. So I have 95.6 plus or minus 2.262. So this is 95% confidence and degrees of freedom equal to 9, times S, which was 13.71 divided by the square root of 10. Let me just double check my math here. Maybe I made a mistake. Oh, yep, I made a mistake. 9.81. 2.262 times 13. Okay, so that would be 79 and 41. All right, is that better? Nobody's saying anything.
Yeah.
Okay. Sometimes I get shattered my confidence here. It's been a rough day for me. All right. So there we have it. So I would say I'm 95% confident that the average IQ of the population is between 85.79, again, let me just write this all out. So based on my sample, I am 95% confident that the average IQ of the population is between 85.79 and 105.41. Okay. Notice I'm making a statement of confidence. It would be wrong, it would not be correct to say there is a 95% probability that mu, the population mean, mu is between, blank and blank. Okay, this is wrong. Why is this wrong? It sounds reasonable, but it's not correct. Okay. Let me here. Do I have a coin? So this is what I always. Okay. Right. Any stabs at why this is wrong? Okay. So think back of what we said, what we mean by probability. Okay. So I'm going to ask you. I'm going to flip this coin, and I ask, what is the probability that the coin lands heads? And you would say 0.5. Okay. Boom. All right. What is the probability that the coin landed heads? You guys are still saying 0.5. All right, what about now? All right, what is the probability that the coin landed heads? Okay, so you guys are still saying 50%. But actually, once I flipped the coin, there was there's no probability involved anymore, okay? Probability only exists for things of uncertainty. Okay. So before I flipped the coin, we did not know whether the coin would land heads or tails. After I flipped the coin, you still don't know whether it landed heads or tails, but there's no more uncertainty here. There's no meaning to the question of what is the probability here, because probability only exists for events of uncertainty, okay? So all you can say is, I'm 50% confident that the coin landed heads, or I'm 50% confident that the coin landed tails, but the fact of the matter is that the coin either landed heads or it landed tails. There's no probability involved. Yes?
So what you're saying is that the probability has to do with the actual outcome, and what we're dealing with here is just the likelihood that the outcome is what we think it is?
I'm trying to understand. I want to say yes, but I'm still processing the question. Let me just finish my explanation here. So if there's no uncertainty involved, there's no sense in asking probability here, okay? And that's what's going on here. The mean of the population is some number. The population has some mean. That's a property. There's no uncertainty about the mean of the population, okay? The mean of the population is some number and it's fixed. We just don't know what it is, okay? There's no uncertainty about the mean of the population, so there's no sense in saying there's a probability associated with that, okay? Just like saying there's no uncertainty about how this coin landed. You guys don't know how it landed, okay? But there's no uncertainty about it. So it doesn't make sense to talk about the probability of how the coin landed. All you can say is make a statement about your knowledge, which is basically what we're saying when we're saying, I'm this confident. Okay? So there's no uncertainty about the mean of the population. The mean of the population doesn't care what a random sample looked like. The mean of the population is mu. What we see, what we do with our random sample and the confidence interval we make, the mean of the population doesn't care. Mu is not going to change. Okay, so mu is fixed. It's a property of the population. Okay, there's no uncertainty. About it, so no probability. On the other hand, we don't know what mu is, and so we have to make a statement of confidence. And this statement of confidence is based on our understanding of sampling distributions. Just like you don't know how the coin landed, but you can make a statement of confidence. You can say, I'm 50% confident that the coin landed heads. Okay? And that's based on your understanding of how a coin landed, or how a coin lands. Okay? It landed tails, by the way. Okay, so this statement is not correct, okay? Is that explanation all right? Okay, so you always want to say, I'm 95% confident that the average, of the population, okay? It's not about the sample, it's not about future samples, it's not about individual values, it's about the mean of the population. That's an important thing. Yes?
So basically, you make this attributes take out probability. So I'm 95% confident that the population.
Yes. So if we scratch this out and we say I'm 95% confident that the population mean is between here and here, that would be correct. Okay. At least this is how it works with our classical view of statistics. Okay. And so, but sometimes you'll see people misinterpret the results of a confidence interval. And so I'm just warning you to that, okay? Yeah, so probability only makes sense when we're talking about things of uncertainty. But what does it mean to say I'm 95% confident? Why am I not 99% confident? Or what would it mean to be 90% confident? Well, okay, so if I wanted to be 90% confident, if I said, well, I don't need to be 95% confident, I can just be 90% confident, what would happen? with my interval? Would it get bigger or would it get smaller? It would actually get smaller. Okay, when we decrease our level of confidence, our interval gets smaller. Okay, so just imagine, I don't know, a bad guy on the run from the cops. Okay, and there's like a chase.